Hello, we're going to take a look today at the Student Multivariate Calculus package. I want to demonstrate, explain what the functionalities are, and point out what new functionalities we've added in recent years. Now, if you go up to the help page on the package, they will be grouped, the functionalities are grouped into visualizations and interactive. I prefer a breakdown into functionalities. So let's look over here, way back in Maple 11, that's some 9 or 10 years ago, the original shape of the package. It had, I'll go down to the bottom here, it had 19 commands. Now compare that to some of the other student packages. For example, Student Calculus 1 has 55 commands, much richer. Vector Calculus, 66 commands. Student Linear Algebra, 89 commands. So this package started its life very sketchy. So it is a group of 5 tutors. Now, this group of 5 tutors has remained 5 tutors throughout the timeline. They are in a shaded color rather than black to indicate that from the very beginning, or at least as far back as I can trace it, they were accessible through the context menu. So you could access the tutors from the Tools menu, Tools, Tutors, Calculus Multivariate, and you could access the tutors from that menu. But if you access them through the context menu, then the item that you clicked on is incorporated into the tutor so that you don't have to enter the new data into the tutor. So these 5 tutors have a certain functionality. The approximate int tutor does Riemann sums for a function of 2 variables, f of x and y, and it works only over a rectangle. But it draws pictures, so there's a certain utility there. Cross-section tutor. With the cross-section tutor, you visualize plane sections, level curves. That's a useful tutor. There's a directional derivative tutor. It will compute a directional derivative, try to draw some pictures that are representative. There's a gradient tutor that, again, it will compute a gradient and draw some pictures of what a gradient vector looks like. And there's a Taylor approximation tutor. That's a pretty useful tutor. It will also draw some pictures of surface with various Taylor approximations. Next functionality is integration. And so you see that there is an approximate int command upon which the approximate int tutor is built. And then there's the multi-int command. Multi-int command creates the double or triple iterated integral. It has a syntax different from the int command at top level, but the output of that command is either the evaluated value or the unevaluated integral, or the value computed stepwise, and you can see all various steps of the computation. So something has been added to that command. Now if you go across the timeline, what you see here, okay, so in the previous version, Maple 2015, you see here I've written multi-int, meaning that the multi-int command became accessible through the context menu. And in the present version, the multi-int command has been augmented to recognize the predefined regions that were known to the integration commands of vector calculus, on student vector calculus. And I'll take a look at that later, but you see it's in black, which means that that augmentation has not yet made its way to the context menu. In spite of the fact that in the context menu system, if you load student vector calculus, you can access the line int command and the path int command. Path int does a line integral of a scalar, and line int does a line integral of vector, tangential component of the vector. And that context menu application gives access to the predefined regions, but that has not been done for multi-int. That's why it's still in black here. So there's the multi-int command. That's a useful command in the package. There are a couple of other integration commands. Center of mass. So the center of mass so if you have a function of 3 variables or a region in R3, the computation of center of mass requires that you have 3 moments and the total mass, and you have to divide appropriately. So these are 4 different integrals that you have to set up and evaluate and manipulate. This command will display those and evaluate them for you. In two dimensions, the center of mass command will do the appropriate integrations and also try to draw a picture of what it is that you are computing and where the center of mass lies. There's a function average command which will compute the average value of a function of several variables. It's interesting that there is no tutor for that, although in calculus of a single variable, there's a function average command and a corresponding tutor. And then there is surface area command. It will compute the surface area of a given surface. It is smart enough to figure out the element of surface area, so you don't have to figure that out yourself. And then there's a change of variables command. It will do a change of variables on a multiple integral, 2, double, or triple. So it makes the appropriate substitutions into the integrand, and it inserts the appropriate Jacobian, but it really can't handle the boundaries. And that's the hardest part of the changing variables in a multiple integral, is describing the region in the new coordinate system. And so the boundaries are left in the original coordinate system until the integral is evaluated, and then you have to go back to the original variables and make the substitution of the boundaries there. So it's a difficult problem to deal with. The revert command is the command that undoes the change of variables. Then under optimization, there are 2 commands. Lagrange multipliers, that's for constrained optimization, and then for unconstrained optimization, there's a second derivative test command. Now, if you look way over on the right, in the present version of Maple, the Lagrange multiplier command has become available through the context menu system. But the second derivative test command, which tests a critical point, or multiple critical points, for whether they are max, mins, or saddles. initially, the package did not address a major chunk of the multivariate calculus course. Most of those courses begin with a section on lines and planes. There's an introduction to vectors, and then you dabble with lines and planes, and then attempt to get the student to think beyond R2. Get them to start visualizing what happens in R3, because lines and planes are linear things. Well, in Maple 17, we added commands for addressing lines and planes. So way at the bottom here you see line and plane. Those two commands create objects. I think in Maple the fancy name is a module, a line object and a plane object. And so the line object is this container that holds all the information about a line, and the plane object is a container that holds all the information about a plane. And then you can interact with these other commands. So you can ask if two lines are skew, if they're parallel, or two planes are parallel. You can ask if the line contains a certain point. You can ask if the plane contains a certain line. You can ask for the distance between a point and a line, a point and a plane, a line and a plane, two planes, two lines. You can ask if two objects in the line-plane world are equal. Get dimension is a programming command for figuring out if you're in the plane or if you're in 3-space. You can get the direction vector on a line. You can get the intersection of, say, a line and a plane, or two planes if they intersect. See, down here, this is an interrogation. Do these intersect, yes or no? And then if they do, then this would tell you what is the intersection. You get a normal from a plane. You can ask for a graph of a line or a plane. You can get a point on a line or a plane. If you have a plane object, you ask for the representation, you get the equation of the plane. If you have a line, well, there are multiple representations for a line. There's a vector, parametric, symmetric. So you ask for the representation, and you choose what representation you want. So that came into existence as commands at the same time it was put into the context menu. So all of this stuff on lines and planes can be done point and click through the context menu. At the very top, you see this little period. And that represents the first attempt in the package to provide for a dot product. When you're dealing with lines and planes and vectors, in that first unit in the multivariate calculus course, you need to be able to do a dot product. And that was never addressed, so students would have to load additional packages, linear algebra, or vector calculus, each of which had its own drawbacks. If you were working in linear algebra, then you were working over a complex field. And if you were in vector calculus, then you had vectors, and vector calculus have a special representation. It was just a mess. So what was sorely needed was a dot product over the reals in the package, so that you wouldn't have to go outside the package to do that kind of a calculation. And so that finally addressed in Maple 17. And you can see going across the timeline, it shortly became obvious that a couple of things had been missed in constructing this material on lines and planes. The angle between two vectors and the angle between two planes, that had been missed. There was an angle command, a vector angle command in either or both linear algebra and vector calculus, but it belonged in multivariate calculus. The question, are orthogonal, or are two vectors orthogonal, or two planes orthogonal? And finally, the projection. So projection requires dot product, so there was the dot product, but still there was a need for a projection command, which is project this onto that, right? Do an orthogonal projection of a point down onto a plane or onto a line, or project a vector onto a plane, vector onto a line. And so that was finally addressed in April 18. So then the next category, I just pick vectors, gradient vector. That's the command that was used to build the gradient tutor. And directional derivative. So the directional derivative command, it has a unique feature in that you give it the function you want to take the directional derivative of, and a vector in the direction that you want to measure in. But that vector does not have to be normalized. The command does the normalization for you. So that's a very interesting command. And in the timeline going across, you're looking at what changes to vectors. Finally, this is Maple 12, this is Maple 11, this is Maple 12, a del and a nabla was added to the package. So now there were, at this point now, 21 commands. So the del and the nabla, you had to type del, nabla, nabla, because the other packages like vector calculus had those commands, and if you wanted those to use del for getting a gradient, well, the del and the nabla are basically two different names for the same thing. You had to go outside the package with the consequences of the objects in those other packages are incompatible in some senses with the objects in the multivariate calculus package. So that was added, and then you can see up here the dot added for dot product. Going across the timeline, the gradient command functionality was added to the context menu. Okay, so it's not a new command, it's just that this indicates that Maple 18, the gradient was accessible through the context menu. And this is Maple 2015, the directional derivative became accessible through context menu. And finally, in this version, the most recent version, a norm and a normalize command was added. Now, these two commands, norm and normalize, are available in linear algebra and vector calculus, again with the complications of going outside the package. In linear algebra, you got to worry about the field over which these things take place. Maple defaults to complex field in one instance. So those commands now in the multivariate calculus package default to the Euclidean norm over the reals, which is what students at that level expect. And right here you see diff. It's not a command added to the context menu, although it's in the shaded color there. What that means is the diff command in vector calculus is modified to map automatically onto the components of a vector. So if you have a curve described by a vector and you want to get a tangent vector, you want to differentiate the components. At top level, you have to use the map command to map diff onto the components. In vector calculus, that mapping is automatic, so you just take the derivative. Well, why should we have to go outside the multivariate calculus package to get that same property? Why introduce vector calculus just to get that property? So finally, diff in multivariate calculus got that same modification, so it maps automatically onto a vector. And finally, a dot product and a cross product command has been added to the package. And the reason for adding the command to the package is that without the command in the package, you can't bring it into the context menu. So now you can do a dot product and a cross product through the context menu. And a final pair of commands, but they're two different names for the same functionality, box product, triple scalar product. That's A dot B cross C. And then you see here the notation ampersand X for a cross product. That's what you would type if you were typing in one-dimensional math for a cross product. So here you have the dot for dot product finally got added. And over here you see ampersand X. And those things existed in other packages. They just needed to be brought into this package. And down here in miscellaneous, I've got listed the cross-section command on which is built a cross-section tutor. The Jacobian command, maybe I could have put that up with integral. The Jacobian command, which would either give you the Jacobian matrix or its determinant, which is the true Jacobian. And the Taylor approximation command, upon which the Taylor approximation tutor is built. And you see way over here that the Jacobian has been now made accessible through the context menu. And you can see here the growth of the package from 19 commands up here now to 48 commands. So now let's take a look at some of the computations that you can do with this package. So I think I'll bring back my palettes here. So the first thing I want to do is I want to load the student calculus, a multivariate calculus package. So tools, load package, student multivariate calculus. All right, I'm going to look at two of the tutors. I'm going to look at the cross-section tutor and Taylor approximation tutor. Okay, so I typed in something that I'm going to look at through its level curves and plane sections. So I right-click on that, and down here, because I loaded the student multivariate calculus package, I go down to student multivariate calculus, tutors, and I'm going to look at cross-sections first. So now the cross-section tutor comes up, and the expression that I clicked on is already in place. I don't have to figure out a way to get it into that little box. So this is a default here. Z here, 0.32 here. So what this means is that you're going to see 5 cutting planes, Z equals a constant, and those 5 cutting planes are between 0 and 32. Now if you look over here at the scale on the Z-axis, it's down as low as minus 100, and you know from here it's going to go up as high as 10. So this needs to be changed. So if I change it to minus 90.8 and say display, I will see those level curves. There is a contour map, there are the cutting planes. So you now have level curves. If you want plane sections, well, you could say, for example, x equals 2, and say display, and you get the plane section at x equals 2. But you can also do something like this. X goes from minus 4 to 4. Let's say minus 4 dot 4, and let's increase the number of planes. How about we do something like 15, and then say animate. And so what will happen is you'll see an animation of that cutting plane, x equals constant, slicing through the surface, giving you a moving plane section. And you can do that for y. You could also have done that for z equals, and you would have had the same effect of the cutting plane moving up and down. So this is, in my opinion, a useful tutor to begin a student's thinking about the meaning of a plane section and a level curve, because it does the graphics in a painless way. You just got to fiddle with a few numbers, do a little point and click, and you have the graphic. Taylor approximation. So again, I have a function here, and I want to get Taylor polynomial approximations. So Student Multivariate Calculus tutors, Taylor approximation tutor, tutor launches. There is the expression. Default point of contact or point of expansion is 0, 0. Let's make that 1, 1. And rather than defaulting to a degree 5 polynomial, and I've only got a quadratic, I'm going to degree 1 approximation. And this is, to me, one of the more useful pictures. You got a sketch of this piece of the surface. There's a little green dot here, which probably doesn't come across through this WebEx broadcast. That little green dot is the point of contact 1, 1. And the first degree Taylor polynomial is the tangent plane. So z equals to this stuff is the tangent plane contacting here at 1, 1. I think this is a useful tutor. All right. Now let's take a look at multi-int. We'll do some work with multi-int. So first of all, here's a table that shows the predefined regions that multi-int can deal with. And here you see the syntax for how you set that up, because at the moment you can only do this with a command. You can't do it through the context menu yet. So multi-int, here's the function that comes first. Because this is a scalar and scalars don't carry a coordinate system, Maple needs to know what the variables are. So that's why you have this list of variables, x, y, which indicates the order in which you intend the integration to take place. So you can say circle, ellipse, and you can define the ellipse either by an equation or by a center and major minor semi-axes. And theta is the angle of rotation of the major axis. Then sector applies to circle or ellipse, meaning you want to do a part of the circle or ellipse. And this is the starting and the ending angles. Rectangle, very useful. Triangle, well, you want to integrate something over a triangle, unless the legs of the triangle are parallel to the coordinate axes. You have to integrate with two separate integrals because the boundaries change at a certain point. As you pass one of the vertices, the boundaries change. So by being able to just tell Maple, I'm integrating over a domain in the shape of a triangle, and here are the vertices, right? V1, V2, V3 are the vertices, you give them as vectors. Maple figures out the equation of the edges of the triangle and represents the two integrals that it will take just the way it would have been in the vector calculus packages, either the student or the main package. Very useful, very, very helpful. General region, where you integrate from one curve to another, either in the vertical direction first, or here you're doing it in the opposite order. X is a function of y. You notice you have to make an accommodating change in the order of the variables here. And over here it shows you what kind of an integral you're getting. If you do it this way, you're getting dy dx, and if you do it this way, you're getting dx dy. So that table indicates what's available with commands. Let's just do one of them. So we have multi-int. How about x, y? And then you need x comma y equals, how about ellipse? And let's give the ellipse as an equation for y squared equals 1. Now, we're going to show you what happens if you just use this very simple syntax. And I'm going to do output equals integral. So, Maple switches to a polar coordinate representation, but it uses the variables x and y. But x is actually r, and y is actually theta. That's very confusing. And so, if you put r theta here, then Maple uses an r and a theta, and it's not quite so confusing. And so if you check out the conversion of this to polar coordinates, right? This becomes r squared cosine squared. This becomes 4r squared sine squared. You factor out the r squared, and you solve for r. Take the square root, okay? Well, here Maple uses tangent, but if you follow through, you would have had sine and cosine. And here, if you convert this to sine and cosine, you'll see that that's really all that has happened. Okay, so multi-int, useful. And if you change this to output equals steps, then Maple will execute the integration, and it will show you the steps involved. Right? So first you do the inner integral, and you evaluate at the endpoints. So that gives you the outer integral to do. This is the outer integral. This is the antiderivative. You have to evaluate at the endpoints. But we knew that this was going to be 0 because of the symmetry. We had x, y, symmetric, anti-symmetric. Over a symmetric region, we knew the answer was going to be 0. So now, Lagrange multipliers. Right? So this is accessible now through the context menu. So xy is the objective function. X squared plus y squared minus 2 is the constraint function. So if you right click and go down to Student Multivariate Calculus, you will see that Maple says, well, this combination means can only be interpreted to mean that you are looking to do a Lagrange multiplier problem. You must tell it what are the variables, because you could have a parameter, right? There could be an a as a parameter in there somewhere. Okay, so you need to tell it the variables, and then here you have the option of getting the value, which just the answer, the pairs x, y that satisfy this problem. Detailed means you get a little bit more information. You get the value of the Lagrange multiplier and the function value at the critical points, or you can get a graph. All right, so let's do detailed. Let's see what you get. All right, so you get x equals y equals and the value of lambda, and then you get the value of the objective function xy. So it's 1 here, minus 1 here, minus 1 here, 1 here. And let's go back and see what the graph looks like. Let's have, you gotta put x and y back again, and let's see what happens if we ask for the graph. So this is the graph, okay? So these two planes represent the plane where you have the high values 1 and the low values minus 1. This here and here you see pieces of the saddle surface xy. Unfortunately, in my opinion, the constraint x squared plus y squared minus 2 is drawn as a surface in 3 dimensions, that to me is not helpful, right? Because what you really want is the set of level curves. That's what these green lines are, level curves of the objective function. What you really want to see is the constraint curve, and you want to see it tangent to level curves, because those are the points of tangency are what the Lagrange multiplier method finds. But there is some utility in graph, and there it is. Okay, I'll do one example in this section on lines and planes. This is a typical problem, lines and planes. Plane through 3 points. So I pre-typed the 3 points because in Maple points are lists. Right-click, Student Multivariate Calculus, lines and planes. The only thing you can do with 3 points is the form of plane. So Maple says, what do you want the variables on your plane to be? Defaults to X, Y, Z. You either change it or you say, okay. And this is what I mean about a plane object. See, this is 2 wedges in plane 1. It's just a representation of the name of the module that contains all the information about that plane. Then you right-click on that, and you go down to lines and planes, and now you see you could get a normal, a point on the plane, generic representative point on the plane, or the representation. If you get the representation, then you get the equation. All right. If we had gone here to lines and planes and said, okay, I want the normal, then you get this vector. And if you say, I want a graph of this thing, then you get a graph of the plane. I think the axis system always looks better if you go to framed, okay, less cluttered. You get a representative point, and you get a normal vector, okay? And then for vector operations, vector projection, okay, so what I did was I did a control equal, which is equivalent to going up here and saying evaluate and display in line. See right here, if you do the right click on here, the context menu doesn't know what these 2 things are yet until they are evaluated. So now it knows what they are. And under lines and planes, you could see Maple says, okay, we've got 2 vectors. You might want the angle between those 2 vectors, or you might want to project the first onto the second. If you want to project the first onto the second, you get projection. Okay? And then box product, well, A dot B cross C, triple scalar product. So see, that's what I mean. If you right click, you don't even see Student Multivariate Calculus because Maple doesn't, the context menu doesn't know what these objects are. It has to be evaluated for Maple to say, oh, okay, vector, Student Multivariate Calculus. And the only thing you can do with 3 vectors is to get the triple scalar product. So there's the triple scalar product. And if you wanted to do that from first principles, I'll do a little copying and pasting here. Let's copy this is the first vector. And we want a dot product. So I'm going to use this dot product from my favorites palette. And there is common symbols. All right, and that's the dot product that I'm taking, and here's the cross product. And what I've done is I've right-clicked on those things, added it to my favorites palette. That's how I populate my favorites palette. There's my dot, there's my cross, there's my del. Okay, so then I'm going to open a parenthesis here. I want to take the second vector, B cross. Oops. Cross is in the wrong place. I want it on this side. Cross C. I'll drag this one down, close the parenthesis, and A dot B cross C, which is the triple scalar product, is again 94. So there's a rough overview of the the Student Multivariate Calculus package in its present form. And you can see how it really needed to have things added to it so that it became more self-contained, so that the student who wants to use Maple in multivariate calculus doesn't need to be jumping from package to package. The only place where the student would really want to go to the vector calculus package is if the multivariate calculus course does the Frenet-Serre formalism. If it does curve analysis through the Frenet-Serre formalism, that's best done in vector calculus, and I would argue to bring that formalism, or the machinery for that formalism, into the multivariate calculus package. It's too well done in vector calculus to worry about bringing it over into the multivariate calculus package.